Hello and welcome. My name is Noah Deer. In this video we will be looking at Lesson 15, Double Integrals over General Regions for PCC's Math 254 Vector Calculus 1 course. So in this lesson we will look at type 1 double integrals and type 2 double integrals. These are essentially whether we're looking at integrating with respect to x first or with respect to y first, and we call it a type 1 if it's easier to integrate with respect to y first and then with respect to x. It's a type 2 double integral if it's easier to integrate with respect to x first and then with respect to y. And the reason it's easier to integrate with respect to one over the other is going to be due to the region that we're integrating over. So if it was just a rectangle like before, you can switch between the two without really worrying about anything. But if I have functions, rather, if the region we're integrating over is something where the curves are functions of x or y, then it will be easier to integrate in one direction than the other. We can always integrate with respect to either first, but sometimes we're going to see that it's just easier to do it in one direction before the other. But let's not get in too much of a discussion until we start looking at some examples here. So we'll look at switching between these two types. As I was just saying, we can always switch between them, and we'll use switching between them as a way of looking at how it really is simpler to do it in one direction than the other a lot of the times. We will finally look at volumes of solids, where we are given a description of a solid and then we have to set up the double integral ourselves. So let's go ahead and jump right in here. Section 15.1, type 1 double integral. So far we've only looked at finding the volume under a surface that's over a rectangular region in x and y. Over a rectangular region in x and y, not a other shaped region in x and y. In those situations we found constants for our bounds in both the x and y directions, and that we could switch whether we were integrating with respect to y first and x second, or vice versa. That is, we found that integrating f of x comma y over the region from a to b in x and c to d in y is obtained by the double integral from c to d in the y direction of the integral from a to b in the x direction of f of x comma y equals, switch those bounds around, the integral from a to b in the x direction of the integral from c to d in the y direction of f of x comma y. However, if we want to find the volume under a surface and over a domain that is not rectangular but instead bounded by two equations in x and y, that is, I could have like y equals negative x squared plus 1 and y equals positive x squared minus 1. So we've got these two parabolas in the xy plane, and we look at the region between them, and that could be the domain that we're looking at. So that's just one example. We'll see something similar here in this next example. So if this is the case, then we have to give much more care to the construction of our double integral. We look first at situations where it's most convenient to integrate with respect to y first and then with respect to x, which we refer to as a type 1 double integral. We find that this occurs when we are integrating over the region. Let's cross this out. The region bounded between two functions y equals f of x and y equals g of x over some fixed x interval. So lots of words there. You can read it a couple times if you want to, but let's just look at an example to really see what I'm trying to say here. Example 15.1.1. Evaluate the double integral over the domain D of x plus 2y d capital A if D is the region bounded by y equals 2x squared and y equals 1 plus x squared. So to start this off, let's take a look at a bunch of pictures. Okay, so we have y equals 2x squared. This is going to give me, let's see, I've got 4 and 8 up here, so let's do 6, 4, 2, negative 2, and 2 here. So just kind of getting a scale for us to see what's going on. We're going to have the points negative 2, 8, negative 1, 2, 0, 0, 1, 2, and 2, 8. Let's get this drawn in here. So I am going to use GeoGebra 3D in order to better show you what's going on, but if we were doing this by hand and didn't have technology, we could at least sketch these just like this. So 1 plus x squared, that's going to have the point 0, 1. Oh, let's label y equals 2x squared. Let's switch colors to show the other one. So I've got 1 plus x squared, still an upward facing parabola. We've got these 3 points, then I've got 2 over and 4 up gives me this point and this point. So we'll get a parabola. Comes down here. It goes through the points negative 2, 5, negative 1, 2, 1, 2, and then the vertex is 0, 1. Let's switch back, label some of the points on our other curve. We've got at least that one I'm going to label. And back to red. So here we have y equals 1 plus x squared. And the region that we're looking to integrate over is the space between these two curves. And as we start to think about what we're doing in the y direction, we're integrating between y equals 1 plus x squared is above and 2x squared is below. That is, when I'm integrating with respect to y, the function that we're integrating, the surface, is x plus 2y. If I want to do the y direction, which is definitely the easier direction to do first here, I want to go from 2x squared as the lower bound and 1 plus x squared as the upper bound in the y direction. And so let's take this integral and we'll add to it the x direction stuff in a moment. I'm going to leave a bunch of extra space here. In the antiderivative with respect to y, I'm going to give it big parentheses, this is xy plus y, whoops, I said it and then didn't write it, xy plus y squared, and we evaluate this from 2x squared to 1 plus x squared. This then equals, so these are y values that we plug in. We get x plus x cubed plus 1 plus 2x squared plus x to the 4th minus, let's see, 2x cubed plus 4x to the 4th. And then this simplifies down to, let's see, we have an x to the 4th minus 4x to the 4th is negative 3x to the 4th. We have an x cubed minus 2x cubed is negative x cubed. We have a plus 2x squared. We have a single x, and we have a plus 1. So this all simplifies down to negative 3x to the 4th minus x cubed plus 2x squared plus x plus 1. What we really see in order to set up this integral is that because our functions are already given as y equals 2x squared and y equals 1 plus x squared, we don't have to solve for x here. We don't have to do anything weird to get x values in terms of y values. My y values for this region are given in terms of x values. So this is really, this y equals 2x squared, that's my lower y values, and y equals 1 plus x squared, those are my upper, or higher y values. So, but we want to put them as x's so that when we plug them in, we get an expression just in x. So, because both of these functions are input variables of x, this is easier to take the integral with respect to y first. And then we can go ahead and say we want to then integrate in the x direction from x is negative 2 to, or I'm sorry, from negative 1 to 1 in the x direction where these intersections are. If we integrated when x is like negative 2 to 2, then we would also get the space up here or over here and over here And we would get that as negatives because the y equals 2x squared and 1 plus x squared have switched which one is above and which one is below. So that the integral would give us a negative value there. And we don't want that. We want specifically the space in between them, not this open infinite space outside here. So we're just going to do from x is -1 to x is 1 in that x direction. So I'm just going to tack on this -1 to 1 in the x direction in front of everything that we've done so far. And so what we have then is we take the antiderivative, we get -3/5 x to the 5th minus 1/4 x to the 4th plus 2/3 x cubed plus 1/2 x squared plus x evaluated from -1 to 1. And then this equals, let's see, 32 over 15. I just plug that into a calculator real quick to speed things up a little bit and save us some space here. So let's take a look at the GeoGebra graph. So here I've got that graph pulled up, and we can see, so here's -1 to 1 in the x direction, here's 2 on the y-axis. You can see our parabolas that are in x and y, and we're looking for the volume of, it's really hard to see, but here's that x plus 2y is this plane right here. So we're looking for the volume underneath this plane, above the xy plane, that falls specifically between y equals 2x squared and y equals 1 plus x squared. So we're looking for the volume of the space inside this region under here. So really kind of tough to see still, but hopefully this gives us, it's maybe a little easier to see from over here. It's this region right in here that we're looking for. So by setting up this double integral in the way that we have, we get the volume between y equals 2x squared and y equals 1 plus x squared, and between the xy plane and the plane x plus 2y equals z. All right, let's go back here. Actually, I do want to say one other thing. If we are saying x equals like -0.5, remember, since I'm integrating with respect to y first, it's like saying that I'm holding x as a constant. So if I held x to be like -0.5, for example, just as one example, then we're looking at what happens, what's the area underneath z equals x plus 2y between these two y values. So the y values for x is -0.5. We could plug into 2x squared and 1 plus x squared to get the y bounds there, but we're not going to because we want to let x then vary all the way from the -1 to the 1 value. So if I look at the GeoGebra, again, if I type in x equals -0.5 for that specific x value, then we're going to get the area of this plane that we see right in here, kind of tough to see, but see if I can zoom in. We get the area of this plane that is between, underneath the plane x equals 2y and between the two parabolas and above the xy plane. So we get this area here, and then as we let x vary, we'll get all the areas. So say x is -0.25, then we get the area of this region between the two parabolas and the xy plane and the x plus 2y equals z function, and then we would do that across all of these. But first we do it with respect to y, so we get the area from here to here of these two parabolas. So that's why we're setting it up in the way that we are, so that we get the area of each of these regions first from this y to this y, which are given specifically by 2x squared, and 1 plus x squared is the upper bound. So let's go ahead and have you do an exercise here in just a moment. Let me just read this real quick. In the above example, we needed to find the intersections between the two functions in order to determine our bounds on the x. And these were the natural boundaries in the x direction. The next example is going to highlight some of the complications we can run to as we set up our double integral. So I'm going to let you work on this as an exercise, but know that some extra things may happen as we look at the intersections here, but really think about how you want to set up your integral based on the geometry of how the area is cut up. So exercise 15.1.1, set up but do not evaluate the double integral over our domain of x plus 2y dA if d, the domain, is the region bound by f of x equals negative x squared plus 1 and g of x equals negative x minus 1 and x equals 3. So just set it up. Don't worry about the evaluation. We're not so worried about taking the double integral as seeing the geometry of how to set the double integral up. All right. Pause the video. I will work through it and talk you through the solution here once you are ready. And we're back. So let's start by just talking us through the picture here. So I actually had to stop and start over once I realized that part of my region was going to be in this lower portion between x is 2 and x is 3. When I draw the f of x equals negative x squared plus 1, this intersects with x equals 3 at the point 3 comma negative 8. So I needed to change my y scale to allow for that point to show up on my graph. So my scale in the y direction is by 2's. My scale in the x direction is just by 1 still. I drew the line x equals 3 as this vertical line in the xy plane. I drew y equals g of x, which equals negative x minus 1. And so this has a slope of negative 1 and a y-intercept of 0, negative 1. Draw this through, we see that it intersects x equals 3 at the point 3 comma negative 4. Then I draw the y equals negative x squared plus 1, so I get this parabola. I start at 0, comma 1. I go over 1, down 1 in both directions to get my y-intercept, switch back to orange here real quick, of negative 1, 0, and 1, 0. We see that negative 1, 0 is also where this downward-facing parabola crosses through the line y equals negative x minus 1. Keep going, and we see that when x is 2, that our downward-facing parabola once again crosses through the line y equals negative x minus 1 at the point 2 comma negative 3. And then we keep the parabola going, and we see that it crosses the x equals 3 line at the point 3 comma negative 8. So this gives us two regions that we are actually bounded here. So if we're looking for the region bounded by these three equations, there's actually two full regions. So we need to integrate from negative 1 to 2 in the x direction between y equals g of x and y equals f of x, and then from 2 to 3 in the x direction while going from y equals f of x to y equals g of x. So they've actually switched which one's above and which one's below when we're looking at x from 2 to 3. So we have to break this up as two completely separate integrals. My total volume is going to be the integral from negative 1 to 2 in the x direction, from this first intersection point to the second intersection point of the y equals negative x minus 1 with the downward facing parabola. So the integral from negative 1 to 2, and then and that's in the x direction, then the integral in the y direction from negative x minus 1 to negative x squared plus 1, because the lower boundary for this region that we're looking at is the straight line y equals negative x minus 1. The upper boundary is y equals negative x squared plus 1. And we're doing that for the z function, z equals x plus 2y, as what is inside our integral. And then we're going to add the volume for the region from x equals 2 to 3. So we have plus the integral from 2 to 3 in the x direction of the integral from negative x squared plus 1 to negative x minus 1 in the y direction of x plus 2y, which is our z value inside this double integral. So we see for this one, because the parabola is the lower bound and the straight line y equals negative x minus 1 is the upper bound, we've actually switched those bounds of integration for this second integral for the second volume piece that we're looking at. go ahead and look at the GeoGebra graph to see this one more time. Here's my downward facing parabola, y equals negative x squared plus 1. Here's my y equals g of x, which equals negative x minus 1, and here's my x equals 3. So we're looking for both the volume of the bit inside of here, so right in there, and then the volume, looks like some of this is underneath the xy plane as well, which is fine. So it looks like when I'm looking here, this section here is underneath, so that's going to give us a negative volume when we do this integration. And that's fine. This is not saying find the positive volume of some solid. It just says set up but do not evaluate the double integral for the given region. So we're not worrying about signs here. And then we have this region inside of here, which is going to be, again, below the xy plane given by this gray plane, and above our x plus 2y in here. So we would expect, because the positive space above the xy plane is so small, that our final answer here would be negative, since there's much more volume underneath the xy plane than above the xy plane. All right, but we're, again, not evaluating this. All we wanted to do is set it up. So that's our type 1 integrals. Now let's look at type 2 and discuss why it's easier to set up type 2 integrals, or what kinds of functions we're going to see that are easier to set up as type 2. So section 15.2, type 2 double integrals. A type 2 double integral, on the other hand, is a situation where it is most convenient to integrate with respect to x first and then with respect to y. We find that this occurs when we are integrating I did that in the above one. I think I copied and pasted here. So we find that this occurs when we are integrating over the region bounded between two functions, x equals f of y and x equals g of y over some fixed y interval. So now let's look at the following example to see how this is working. Evaluate the double integral of 2x minus y squared d capital A over the region D, where D is the region bounded by x equals parentheses y minus 1 squared minus 1 and x equals 2y. So let's start by graphing these two equations in x and y to see what region we're even integrating over. So if x equals y minus 1 quantity squared minus 1, this is a upward facing parabola in the x direction that has been shifted up 1 in the y direction and down 1, left 1 rather, in the x direction. So we have a vertex of negative 1, 1, and it has not been stretched at all, so we would expect, since it opens in the positive x direction, to give us, let's see, we got 4 here. I'm assuming 1 by 1 first. I may have to go back and edit this. 3, negative 1 here, negative 2 here. Always show your scale on your axes. You don't want to have the reader be confused on what scale it is that you're using. So we should have 8, 4, and 8, negative 2. Alright, so this is y, or no, not y, this is x equals y minus 1 squared minus 1. And then x equals 2y. That is a straight line. Let's change my colors up here. So x equals 2y is a straight line if y is 0, x is 0. If y is 1, then x is 2. If y is 2, x is 4. If y is 6, no, if y is 3, x is 6. If y is 4, x is 8. And so we see our other intersection point there. So we can draw our line now. x equals 2y. It's definitely, I'm going to switch back and label some of the points on my other. We have the 0.84, 0.3302, negative 1, 1. This intersection is very important, 0, 0. And then this would be the 0.8, negative 2. I'm not going to worry about labeling it here. We do have the 0.3, negative 1 here. So then that's fine. I don't need to label any other points on the red line. Switch to green. So the region we're looking at is in between here. And if we could do this as a type 1 where we're doing with respect to y first. If we were doing with respect to y first, the y2 minus y1, the lower bound for my y direction, the upper bound for my y direction would be some square root function, a positive and negative square root that we would do from negative 1 to 0. And then we would do the square root for this parabola, sideways parabola, from 0 to 8. And then the lower bound would be the straight line. So we'd have to set this up as two separate integrals. But if we think about this in the opposite way, we can look, say, at this section where we're looking at, or say right here. So I'm going to do in the x direction first, where the upper is the red line. So this is my upper boundary in the x direction. And the orange line, oops, slight one. This is the lower boundary in the x direction. And if we do it that way, then the upper boundary is always the red line and the lower boundary is always the orange line. So we wouldn't have to set this up using two separate integrals. So the upper boundary is x equals 2y. Note we already have everything solved for x, so I don't even have to change things around when we're doing it this way. The integral in the x direction has a lower boundary of x equals y minus 1 squared minus 1. Right? This is the lower boundary. And the upper boundary is 2y. And we are integrating over the z values 2x minus y squared. And we're doing in the x direction first now. And then in the y direction, let's just do blue, sure. We will do from y is 0 to y is 4 over here, right? These are lower y values, and then we're going upper y values as we move this way. So the integral from 0 to 4 in the y direction. And so this is the integral that we get to integrate here. So let's, sure, I like blue. So this equals the integral from 0 to 4 of, so here I'm doing with respect to x first, we're going to get x squared minus y squared x, and we want to evaluate that from y minus 1 squared minus 1 to 2y in the y direction then, after we do the evaluation. So this equals the integral from 0 to 4. Well, I'm going to do some scratch work to simplify this here. I recommend you probably do the same. Sure enough, this does actually simplify down quite nicely once you do all the steps. It simplifies all the way down to negative 2y squared, if I haven't made any mistakes here. And so this should be pretty simple to integrate. I will show a little bit more. I'm not going to just jump all the way there for you. So I'm going to plug in the 2y to get 2y squared Oh, and actually that makes me realize I think I made a mistake here. Not too much though. 1 second. It looks like it simplifies down even actually to 0 now that I'm looking at it again. So minus y squared times 2y minus parentheses. I get to plug this in. Let's first note that y minus 1 squared minus 1, this equals y squared minus 2y plus 1 minus 1 equals y squared minus 2y. And that's going to be a little bit easier to plug in here. So I have minus y squared minus 2y, quantity squared, minus y squared times y squared minus 2y. And we'll do that with respect to y. So this equals then, so we're going to have y to the fourth minus 4y to the third plus 4y squared. And then we'll have over here minus y to the fourth, which will cancel with that y to the fourth, plus 2y to the third, which will cancel with a couple of them over here. I'll let you work this out. This is just a bunch of foiling and combining like terms. I'm going to double check my math to make sure I didn't make any other mistakes, but I think we get 0 here. Yep, I am getting 0, which makes this next step in the integration really easy. 0 dy equals 0. So let's take a look at the graph and see what's going on, because it's not like there's nothing here. What's happening is that part of our volume is above the xy plane and part of it's below the xy plane. So let's take a look. So here I've got this pulled up in GeoGebra. Sure enough, so here's our section. Let's actually pull this over. Can't even see that intersection. So we're looking at this, the region here to the right of this rightward facing parabola and to the left of this blue plane given by x equals 2y. And so we see a positive volume for this darker green that is above the xy plane, and then we have a volume for this gray, dark gray space that is actually below the xy plane. So if I look at this from the side, we see this volume underneath the xy plane that is down here, and we have this volume that is above the xy plane over in there. So this space between this blue plane and the green surface there that's above the xy plane. And so those end up, interestingly enough, being exactly the same positive and negative volumes that cancel each other out to give us a total volume of 0, which means if we did, well, we could figure out the equation for where the surface hits the xy plane and find the volume above, and then if we wanted to take that and double it, we could say that the total volume of these together, if we made that negative volume a positive volume, would be twice the volume of this up here. But we're not worrying about that right now. Here we're just doing the integral and not worrying about volumes per se. All right, let's switch back and move forward with our lecture. I'm going to give you guys an exercise, exercise 15.2.1. Evaluate the double integral of 2x minus y squared dA over the region D, where D is the region bounded by x equals y minus 1 squared minus 1, x equals 2y, and y equals negative 1. Note that two of these boundaries are the same as the previous problem, so we're just adding one more bit in this, so you'll have essentially some of the same stuff that we're already using, and I just want you to build off of it as opposed to starting from scratch here. So go ahead and draw your regions, see where you need to set up the double integral, and then see if you can't find any shortcuts for going ahead and evaluating it. And I will be back in a few moments to work through the solution with you. And we're back. So I started by going ahead and graphing all of the boundaries. We have x equals y minus 1 squared minus 1. And so that's our sideways parabola with a vertex of negative 1, 1 that opens to the right in the positive x direction, has not been stretched in any manner. So it does have y-intercepts of 0, 0, and 0, 2. And then it has the points 3, 3, and 8, 4, and 3, negative 1, and 8, negative 2. I drew the line x equals 2y again. It goes through the origin and has a slope of up 1 in the y direction over 2 in the x direction. Can keep using that until we see that it intersects with that parabola at 0, 0 and at 8, 4. Kept going to the left, so it also has the point negative 2, negative 1. And then we graph the line y equals negative 1, and so we see that that crosses the x equals 2 y line at -2, -1. It has a y-intercept of 0, -1, and it crosses our sideways parabola at the point 3, -1. So to find the total volume, we have the volume of the region between the sideways parabola and the line x equals 2y that is above the x-axis. That's the region that we already found. And now we have on top of that the region that falls between x equals 2y as the lower boundary and x equals y minus 1 quantity squared minus 1 as the upper boundary. So for this region here, this is my lower x boundary, and this is my upper x boundary. So for this region, we have the double integral from -1 to 0 in the y direction. We see that our lower y value is -1, our upper y value is 0. And then in the x direction, our lower boundary is x equals 2y, our upper x boundary is x equals y minus 1 quantity squared minus 1. And we're taking the double integral of 2x minus y squared with respect to x first and then with respect to y. The other region was what we did before, and that's going to add up to 0, so really we don't even need to think about it when we're taking the integral over this given domain. So we then go ahead and take the integral of 2x minus y squared with respect to x and get x squared minus y squared times x, and all of that evaluated from 2y to y squared minus 2y. I've gone ahead and FOILed out the y minus 1 squared minus 1 and combined like terms to get that. And then once we do that evaluation, we'll take the integral from -1 to 0 with respect to y. So I plug in the y squared minus 2y for x first, and then we'll plug in the 2y for x second as we do our subtraction using our fundamental theorem of calculus. And so we get the integral from -1 to 0 of y squared minus 2y quantity squared minus y squared times y squared minus 2y, close parentheses, minus parentheses 4y squared minus 2y cubed, close parentheses, dy, which equals the integral from -1 to 0 of y to the 4th minus y cubed dy after FOILing and combining like terms. This equals 1/5 y to the 5th minus 1/4 y to the 4th, evaluated from -1 to 0, which equals negative, parentheses, -1/5 minus 1/4, close parentheses, equals 9/20. And we can go ahead and take a look at the graph here. So when we pull this up in GeoGebra, we see that same volume that we had before, but now we also have this volume between the x equals 2y and the x equals y minus 1 quantity squared minus 1 parabolas that is between y equals -1 and y is 0, now that we've graphed the plane y equals -1. And so we see that we do have some positive volume here and some negative volume, and it looks like with our answer being a positive 9/20 that the positive volume here outweighed the negative volume to give us an overall volume that was positive of these two sections here. All right, back. Let's go ahead and go to our next section, section 15.3, switching between type 1 and type 2 double integrals. So in every situation it's possible to use either a type 1 or type 2 integral, although it's often easier to choose one over the other. Let's go through this to highlight further how one can be easier to find than the other. So we're going to take an example that we already did before. We know that its volume is 0, and we're just going to find that again, but we're going to do it as a type 1 double integral, where we take the derivative with respect to y first and then with respect to x. So example 15.3.1, set up but do not evaluate the double integral of 2x minus y squared dA over the region D if D is the region bounded by x equals parentheses y minus 1 quantity squared minus 1 and x equals 2y as a type 1 double integral. So it looks here, I think I'm going to change this so it matches the plane above for your guys' blank worksheet. Here I'm going to change my scale so that I have -4, 4, and 8 in. So my x grid is by 2s. My y scale is just going to be by 1s still. And so at this point, this is just replicating what we'd already come up with before. except for now it's kind of squeezed. So we have a sideways parabola opening in the positive x direction as a vertex of negative 1, 1. As before, it has a x and y intercept of 0, 0, a y-intercept of 0, 2, and it also has the points 3, negative 1, 3, negative 1, and 3, 3. And we have the point 8. Actually, I'm going to move this. 8, 4, which I know is going to be that intersection point again. And it also has the point 8, negative 2, which is not going to be important for this. Let's graph the line x equals 2y. So we're still going to go through this point, and we're going to go through the origin. The space down here in the third quadrant is not going to matter because we're just looking for this space between them. Again, we're just now doing it really the hard way, where we're going to set it up as a type 1 integral. I'm going to FOIL this out just because we know it's going to simplify down to y squared minus 2y. And so again, we're still looking for this region, but we're going to look at this space first, and then we'll look at this space second. When I say this space first, I'm talking about the space from x is negative 1 to x is 0, and then the second space is from when x is 0 to x is 8, the space between these two graphs. And so when I do this, if I want to integrate with respect to y first, I need a y lower bound and a y upper bound in terms of x. And right now I have x in terms of y, not y in terms of x. So we're going to have to do a little bit of work here. Let's look, well, the x equals 2y, this one we can switch around as y equals 1/2 x. That's easy enough. And that, well, for our second section, is going to be useful, but we're not going to use it for the first part of this. This one, x equals the y minus 1 quantity squared minus 1. If I solve for x here, let's move this out of the way, actually, come back for that. Here I can add this one to the other side, so I get x plus 1 equals y minus 1 squared. Take the square root, and I get plus or minus the square root of x plus 1 equals y minus 1. Let's move this a little bit more. Again, we're not going to actually be taking the integral. We already know it's 0. We're just going to see how much more difficult it is to set it up when we try and think of it in the opposite direction. So here we get y equals plus or minus the square root of x plus 1 plus 1. And so when I'm looking at the region between x is negative 1 and x is 0, we see a y upper boundary of a positive square root of x plus 1 plus 1, and a lower boundary, a y sub u, lower y sub l, of negative square root of x plus 1 plus 1. Right? So this bottom half of the parabola, this is given by the negative square root of x plus 1 plus 1. And so my y lower boundary here is negative square root of x plus 1 inside the square root plus 1 outside the square root. My upper boundary is a positive square root of x plus 1 inside the square root, and then another plus 1 outside the square root. So we're doing this first. The 2x minus y squared is inside the integral. So we're doing with respect to y first, then we do with respect to x, and this is from negative 1 to 0 in the x direction. And then we need to add to that the integral. So we'll do in the x direction second. That'll be from 0 to when x is 8. And now we need to find our lower and upper boundaries for y. Now part of this we've already done. My upper boundary for y here, I'll stick with orange. So for the second region, the upper boundary for y is still a positive square root of x plus 1 inside the square root plus 1 outside the square root, but now the lower boundary for my y values is going to equal 1/2 x. So 1/2, or x over 2 is maybe a better way to write that. And my upper is the square root of x plus 1 plus 1. The z values that we're integrating over are 2x minus y squared. And we're doing dy first, dx second. So we could totally calculate the volume this way. We should still get 0. The first region that is to the left of the y-axis, that's totally negative. The region to the right of the y-axis between x is 0 and x is 8, part of that's negative, part of it's positive, but everything should still add up to 0 in the end. You're welcome to plug this into a calculator if you want to, but we will get 0 out of this if we wanted to. So the point of this is that we can switch any of these to the other type, but if we choose wisely, we can make our life a lot easier so that we have less to compute. Okay, so an exercise for you. Exercise 15.3.1, set up the iterated integral, the double integral of y squared e to the xy d capital A over the domain D, where D is bounded by y equals x, y equals 4, and x equals 0 for both orders of integration. So this does not say to evaluate. We just want to see the setup for both orders of integration. And on your blank sheet, you should have a coordinate plane here. I will go ahead and get that added in before I post this. But go ahead and pause the video, work this out on your own, and come back and I will work through the solution with you. And we're back. So I started by going ahead and setting up my coordinate plane. I see as I'm looking at this, I have y equals x, y equals 4, and x equals 0. So I'm quickly seeing I'm just in the first quadrant. So I draw an x-axis that goes from 0 to 4, a y-axis that goes from 0 to 4, and I have the line y equals x in orange, and then I have the line y equals 4 in red. I have the line x equals 0 along the y-axis in blue. We want the region inside between these three lines, so the volume above the triangle with the vertices 0, 0, 0, 4, and 4, 4. So we have that triangle. That's the region that we're integrating over, so we want the volume above this space or below the space if we're underneath the xy plane. And so if I'm integrating with respect to y first, that's my type 1. So if we're doing in the y direction where the lower boundary is here, this equals y equals x, and then this is my upper boundary is 4. So in the y direction I have the integral from x to 4 of y squared e to the xy dy, and then in the x direction we have x is 0 to x is 4. So from 0 to 4 in the x direction, and then this equals, if I switch the bounds now, and if I'm going in the x direction first, then my x lower equals 0, and my x upper equals y, because x equals y if I switch that around. So in the x direction we go the integral from 0 to 4 of y squared e to the xy, and then we take the integral of from 0 to 4 in the y direction of what we get there. And that's my type 2 integral setup. And we're not actually taking this integral to find out what it is. We could plug it into a calculator real quick. This does not look like a fun integral to work through, although I think by parts I could get this to hash out okay. yeah, let's not worry about that. Let's just move on forward here. So in this case, we see that it may not necessarily be easier to do one way or the other, but we still have the choice. So let's take a look at how we may interpret a double integral whose bounds are given as the volume of a solid, and then use this interpretation to change the order of integration. Example 15.3.2, change the order of integration of the integral from 0 to 1 of the integral from x to the fourth to x to the 1/3 of f of x comma y dy dx. Note we're not actually even giving a function, we're just saying a function, whatever it may be. How do we switch this order around? So we're not worrying about whether it's a positive volume or negative volume or anything like that. We just want to see what this is, how this is working. So this is saying that my y lower bound is x to the fourth, and my y upper bound is x to the 1/3. So we want to graph both of those. We see it, x is just going from 0 to 1. I'll put a 1 all the way out here, just because I only care about x's from 0 to 1. So that means this is 1/2. And so let's see. If we look at the lower bound, if x is 0, we get 0. And if x is 1, 1 to the fourth is 1. And let's see, 0 in here. Let's put 1 up here also. So if I plug in 1, I get 1, 1, and my x to the fourth, if I plug in 1/2, I'm going to get something really small. It's going to be like 1/16. So here's 1/2, here's 1/4, 1/8, 1/16 is above that x-axis with this scaling. If I plug in 3/4, I would get 81 over 128, or 81 over 256 is a little bit above 1/4, and then 1, 1. And this will be symmetrical about the y-axis. My y equals, this is the cube root of x. This has the point 0, 0. Let's switch colors here. So we have the y upper bound equals the cube root of x. So 0, 0. And we will have 1, 1 still if y is 1/2 cubed, then x is 1/8. It's right there. If y is 3/4 cubed is 27 over 64 is a little bit less than 1/2. This point 1, 1, and then this will be symmetrical. I'm going to have like right there. Switch to red though. Okay. So this will end up turning over and going down like this, but I'm not concerned with this part of the graph. What we are concerned with is the region between these two, which is here. So as we have this set up, the y lower bound is x to the fourth, the y upper bound is the cube root of x, and we want to switch now where I want this to be the x lower, is the left one, and the x upper is here. And to do that, we solve for x in these, and so the red line was y equals cube root of x. That's the same thing as x equals y cubed. And for this one, y equals x to the fourth, that is going to be the fourth root of y when we solve for x here. This is the positive fourth root of y, not the negative. The negative fourth root of y is the stuff over to the left of the y-axis. It's the part of the, if I look at the graph y equals x to the fourth, it's symmetrical about the y-axis. The part of it that's to the right of the y-axis is the positive square root when we solve for x. This part of that graph that's to the left of y-axis is the negative fourth root of y once solved for x. So we just care about the positive here. So to switch these bounds then, my x direction is going first. The lower bound is y to the third, and the upper bound is the fourth root of y. And the function is inside. And we're doing with respect to x now. Now to do with respect to y, we see that the y values are still just going from 0 to 1. So we can just do the integral from 0 to 1 in the y direction. And let's rewrite the original problem real quick so that we can have a complete statement as opposed to just an answer floating out in the middle of the page. Always good to have complete thoughts as opposed to just floating thoughts. And so we see the original double integral from 0 to 1 of the integral from x to the fourth to x to the 1/3 of f of x comma y dy dx equals the integral from 0 to 1 of the integral from y to the third to the fourth root of y of f of x comma y dx dy. And so we have switched that order of integration. All right, 15.4, volumes of solids. So far in this lesson, we've described a double integral with a region over which to integrate and have seen answers that are both positive and negative depending on how much of the enclosed volume is below the xy plane and how much is above the xy plane, since integrals give volumes under the xy plane as negative volumes. Now we're going to look exclusively at positive volumes that are described via the equations of the surfaces which bound them, and then set up the integral ourselves. Okay, so let's just take a look at an example here. Example 15.4.1. Determine the volume of the solid bounded by the cylinder y squared plus z squared equals 4 in the planes x equals 2y, x equals 0, and z equals 0 in the first octant. So let's take a look at my xy plane and how we want to set this up. My cylinder has a radius of 2. It's free to move in the x direction. It's a circle in the yz plane. So if my z-axis were coming up here, then we would say, okay, we've got a radius of 2 in this direction. Here's my z-axis. And we're bordering this with x equals 2y, which has a, we're just going to go here. We want the first octant only, so I'm not going to worry about anything to the left of the y-axis. Whoops. This line would continue, but we're not concerned about it. This is x equals 2y, x equals 0 is a little bit redundant since we're in the first octant. First octant meaning x is positive, y is positive, and z is positive. So in the end, this ends up not being too different than anything we've already looked at, except now we're given everything in terms of its description, as opposed to just saying, here's a double integral with a region, set up the region. This actually isn't redundant with the x equals 0 if they would have given us x equals 1 per se. So what's this point? This is y is 2, this is x is 4, so we have the point 4 comma 2 here. If they would have given us, say, x is 2, then we would have been looking for this region in here, as that would give us our boundary, but that's not what they said. It says x is 0, so that's going to tell us this region in here. If it would have said x equals 4, it would have been the region over here. So again, not redundant, just thought it was at first. So we're looking for this, the volume above this region in the xy plane and underneath the cylinder, given by y squared plus z squared equals 4. Now, since we're above z equals 0, when I solve for z here, I get z equals 4 minus y squared, and then we take the square root thereof, and we want the positive square root because we want the stuff above the xy plane. So now we can set up our volume equals a double integral. Let's see. What do we want to do first? Since this is a triangular region, it's not going to matter whether I do in the x direction or y direction first. I think I just generally like doing in the y direction first if I can. So I have a lower y boundary of y equals 1/2 x and an upper y boundary of y equals 2. So I have 1/2 x is a lower boundary, 2 is an upper boundary. Inside the square root, or inside the integral, we have the square root of 4 minus y squared. We're doing with respect to y first, and then we'll do with respect to x. In the x direction, we are just going from x is 0 to x is 4. And we got some Christmas colors mixed with orange for some reason. That's all right. Let's just stick with orange as we do this. This here. Now this is not the easiest integral to take, but it can be done with a little substitution and then a trig identity. So we're going to let y equal 2 sine of u. So dy equals 2 cosine of u du. And so we get the integral from 0 to 4 still. And we're not integrating anything yet. We're just doing some substitution. These bounds are going to change here. So these are going to be some weird arc signs. That's fun. Let's see. We'll get there. I'll get those bounds in a moment. We have the square root now of, actually, so the dy becomes 2 cosine of u square root of 4 minus 4 sine squared of u du. So if y is 2, get 2 equals 2 sine of u. So that's when u is 0. And, oh, no, not 0. No, that's when u is pi over 2 is going to give me my greatest sine output of 1. So pi over 2 when y equals 2. If y equals 1/2 x, then we'll get 1/4 x, where u equals sine inverse of 1/4 x. See how that works out here in a little bit. This is going to simplify down. Let's do this over here. I've got, first of all, 4 minus 4 sine squared of u. This equals 4 minus, well, I'm going to factor out the 4 actually. So I've got 4 times 1 minus sine squared of u, but that's cosine, so this equals cosine squared of u. We're taking the square root of this. Oops, I forgot the 4 here. This is the square root of 4 cosine squared of u. So this equals 2 cosine of u. So when I plug that in for my square root over here, this, I've got my double integral from 0 to 4, my integral from sine inverse of 1/4 x to pi over 2. And then we have 2 cosine of u times 2 cosine of u is 4 cosine squared of u. Lagging here. Oh, I need a dx on this still. Du dx. And then we're going to use a double angle formula that tells us that cosine squared of u equals cosine of 2u plus 1 over 2. And when I plug that in here, this then equals the integral from 0 to 4, integral from sine inverse of 1/4 x to pi over 2. Might multiply the 4 by this, I get 2 cosine of 2u plus 2 du dx. So hopefully that's some good integration review using trig substitution. If you're not following all of that, it's not the end of the world. We could plug this into a calculator. I'm just showing you that we could do this by hand also. So here I have the integral from 0 to 4, and then the antiderivatives. Here I've got antiderivative of cosine is sine of 2u, and the 2's good, plus 2u, this evaluated from sine inverse of 1/4 x to pi over 2 dx equals I think I'm about to the point where I'm ready to put it in a calculator now. When I multiply by the 2, that's not going to allow me to take a inverse here. So I have the integral from 0 to 4 of sine of 2 sine inverse. This 2 right here is getting in my way. 1/4 x. Oh, I want to do the pi over 2 first, don't I? So if I plug pi over 2 in, that sine of pi is 0. So we have 0 plus pi minus sine of 2 sine inverse of 1/4 x minus 2 sine inverse of 1/4 x dx. Move this out of the way. There we go. And yeah, I have no desire to try and hash out this inverse sine stuff. We know the derivative of sine inverse is 1 over the square root of 1 minus x squared, I believe, or negative thereof. But with this sine inverse inside the sine, let's just say, all right, we've tried pretty hard here. Let's go ahead and plug this into a calculator. So it looks like if I would have maybe done something else, we would have gotten a little bit easier integral, but let's not worry about it. This is an exact answer of 16 over 3, which is what's telling me that something here could work out nicely. I'm wondering if I would have done with respect to x first and then with respect to y, if this would have hashed out a little bit nicer, just because we have the y inside here, so we're trying to do that right away. But I have this feeling that that's not quite the case, and we don't need to look at that right now. This video's getting long enough, yes? So you can look at that GeoGebra graphic if you'd like to, but let's move on to the last exercise for you guys of the lesson, exercise 15.4.1. Find the volume of the solid bounded by the cylinder z equals x squared, y equals x squared, and the plane z equals 0 and y equals 4. Again, see if you can't do the integral by hand, but if you are getting stuck and it's feeling like that this should just be something that you can plug into the calculator, just do it. All right. Go ahead and give that a shot. Pause the video. I'll be back to work through the solution with you in just a few moments. And we're back. All right, so this one didn't work out to be nearly as painful as the last one. It's kind of nice. So I'm graphing y equals x squared, our parabola that goes through the points negative 2, 4, 0, 0, and 2, 4. The line y equals 4 has a y-intercept of 0, 4. And we see the intersection of these two lines is at negative 2, 4 and at 2, 4, and we're looking for the volume of the region above the xy plane and below z equals x squared. You can see that things are symmetrical. I didn't actually use that at all, but we could use some symmetry to evaluate this in some way. So in the x direction, we're going from -2 to 2. In the y direction, we're going from x squared to y equals 4. So I'm doing the y direction first, my lower bound being x squared, my upper bound being 4. So my volume is going to be given by the integral from -2 to 2 in the x direction of the integral from x squared to 4 in the y direction of x squared dy dx. So taking the antiderivative with respect to y, we get the integral from -2 to 2 of x squared y evaluated from x squared to 4 dx equals integral from -2 to 2 of 4x squared minus x to the 4th dx, which equals 4/3 x cubed minus 1/5 x to the 5th evaluated from -2 to 2 equals 32 over 3 minus 32 over 5 minus -32 over 3 plus 32 over 5. Here we're seeing that symmetry because now we're doubling things. This equals 64 over 3 minus 64 over 5, which equals 320 minus 192 all over 15 equals 128 over 15, which is 8 8/15. Again, you're welcome to look at that graph in GeoGebra, but we're going to leave it at that for the lesson for the day. Thank you so much for watching, and we will talk to you in the next lesson. Have a good day. Bye.